Hello, good morning. Welcome back to the class from the long weekend. This is ECE451 and today is Wednesday. I said you're just coming back from a long weekend, right? So everything good? Yeah, everything must be good. And this week we only have this one-time class. Then next Monday we will have next class, and after today's class we will have some homework, just 2 or 3 problems. I give you 2 problems. I think that will be enough. The topic is related with today's material, that is stability of system. So I think most of you should be already familiar with it, right? Okay, let's see what we will do today. It's ECE451. This is the 3rd week and Wednesday, actually the only class on the 3rd week. And today we will consider the system, whether the system is stable or not. We consider stable system. Stable system. The system, there will be I just suppose like a g of s is the transfer function. This is r of t. This is y of t. So a stable system is a system looks like this for any input r of t. If r of t is bounded, then the output y of t must be bounded. So like this. So what is stable system? It's just like this. We call this the BIBO stability. BIBO stability. Of course, this is a LTI system, right? LTI system, linear and time invariant system, and G is the transfer function. It's a transfer function, right? Things like that. Okay. So how to determine the system to be stable, or what kind of feature can we have for a stable system? Yeah, this question actually same thing. We will see. It will be same thing. The output. We know what is the output. In the S domain, the output is transfer function times the input. In S domain, when you write the equations, write formulas. If your formula is in S domain, then you only have S, no T. If you have equation in a time domain, then you can only have T, no S. Don't put both S and T in one equation. That's wrong. All right. Yeah. We know in the S domain we have this relation. So in the S domain we we perform the inverse Laplace transfer, and we go back, we will have equation in time domain, right? So this is what? In S domain is multiplication, then you go back, there will be convolution. And this is a very important feature for Laplace transform. Yeah, it is also the feature of Fourier transform, right? We have similar thing. So this is a convolution of these two in time domain. There will be 0 to t, and here I put which one in front? I put the g of t. Right, g is here, g, but this is not t. I use another variable tau, and then r of t minus tau. D tau, right? We have this. Now R is bounded. RT is bounded. That means absolute value of r of t were smaller than k for some constant. This k must be a constant. We call it bounded, right? What is bounded? So for any t, the k, you have a bound for. K is a bound of this r, right? This is a bound of r of t, right? It's a constant. It's a bound. We don't know what it is, but there must be some number, right? Some number, like you consider a cosine. If r of t is a cosine of t, then that k is just 1, right? Cosine or no more than 1. You need a little bit larger. If I put equal, then you can choose 1, right? If you do not choose equal here, then there will be k will be 1 plus something, a little bit larger than k, larger than 1. Right? Okay, then you plug in here, then we can have absolute value of y or smaller than the integration is still integration, g is still g, and r will be, you replace r by k, right? By k. So we have this. We can have this one, and the absolute value both are positive. So this one is just k times integration of g of tau d tau. Okay, yeah. G is the inverse Laplace transform of capital G. That is the impulse response, right? Impulse response. This is the g of s to the inverse Laplace transform. Then we have the impulse response. So this is the impulse response. Here's absolute value. Yeah, absolute value. So we have this. So we want, because it's stable, right? It is stable. So this one will be a finite number. If this one go to infinite, then you cannot have a bound, right? This is infinite as a bound. So here we can say integration g of tau d tau, absolute value of g, 0 to t. Now I use infinite. T could be anything, so I use the largest one. This one will be a finite number. So this gives us a condition to check whether the system is stable or not. You check this inequality. If you have this, then the system is stable. The system is stable. Otherwise, the system is not stable. Okay. However, this one looks still not so good, right? You need to do the calculation. You need to find the g of t firstly, and then do the integral, and of course, then you can determine. Can we make it a more shorter way, some shortcut? We do not do the integration, can we? Okay. So this is the next one. Let's see. But what is g? G of t is inverse Laplace transform of g of s. G of s. And if g of s has poles, I say poles, okay, just p. Pi, I run from 1 to some n. The n will be the order of the system. If g has these poles, then we know g of t will be a combination of e to the pit. Yeah, it will be a summation of things looks like this with certain different coefficients. Make sense? Actually, you just perform the inverse Laplace transform of g. You perform partial fraction g of s, the partial fraction then you have G of S equal to S minus P1 sum A1 until S minus, I have n terms like Pn, this An, then you the inverse Laplace transform, you will have G of t, which is e to the negative P1t, right, plus A1 here, until An e to the negative Pnt, right? Yeah. If you have multiple roots, multiple poles, then that means some of them you have some like a square or cube on it, or even higher order in the more powers for some term. Then here you will have some t times before the e to the negative Pit. Right? Yeah. Okay. But then doesn't matter. For this kind of things, G of t integration, the absolute value, then integration, it is a number, not infinite. It's a constant. If all the pi's they have negative real part, we have this. So okay, so this will be the condition to the stable system. G of S is stable. So finally, to check whether a system is stable or not, we just use this. You check all the poles of the system. If all the poles they have negative real part, then the system is stable. The system is stable. Alright. Wait. Sorry, this is positive. Yeah, here's a minus, so here's a plus. Okay. Then they're negative, right? Negative. Well, this is negative. You got it? Any question? I think I need to explain more here. Okay, the result is just like this. You check whether the system is stable or not. You only need to check all the poles. If they have negative real part, then it's fine. Otherwise, it's not stable. That means any of the pi, they have the real part is larger than 0 or 0, then the system is not stable. Okay. This is one thing. Let me see what kind of thing I still need to explain. That'll be fine, right? That'll be fine. You just check the pi. Why we have this one? We say for real pi, e to the positive of Pit will go to infinite if pi positive, and will go to 0 if pi is negative, and we're equal to constant 1 if pi is 0. Right? This is for real number. For complex, pi, I say is a real part ai plus j times imaginary part bi. Then e to the Pit or equal to e to the ai plus bi and j t. So this is e to the ait times e to the jbit. So we have this, right? we have this. We have this one. Okay, you see this one. E to the AI plus JBIT. Right, this is a T. Or equal to E to the AIT times E to the JBIT. This multiplication, the second term, it is just cosine BIT plus J sine of BIT. So this is bounded, right? The both real and imaginary part, the value were no more than 1. There will be the number between negative and positive 1, right? Both. So this number is bounded. And this one, two case. Go to infinite if AI is a number larger than 0. Then go to 0 if AI is a negative value. Oh, I have third case. If AI is 0, it will be just 1. Always 1. Okay. So we have 3 cases. So for this case, stable, we know it is a, the value tend to be 0, so this is bounded. Right. If we have this one is bounded, this one is unbounded. This is unbounded. For this case, well, it depends. It's not. It's still unbounded. Yeah, it's still unbounded. Not bounded. This is bounded. This one is bounded, but when you take integration, right? Our way to check the stability, we need the integration. We need this one. We need integration smaller than infinite. This case, if AI is smaller than 0, this one you do integration from 0 to infinite. It's still finite, still finite number. So this one, it is bounded, and the integration is smaller than infinite. Right? We have this, and these two, you do integration, they were infinite. This is itself is already infinite. You do integration, of course, still infinite. And this is 1. The integration of 1 integral, right? You have this 1, always 1. So the integral, you take integral, you have the area below it, right? This is also infinite, right? The area below it, because the time is go to infinite, right? So the area is infinite. So this one, you take integration, you check this one, it will be infinite. So these two cases, you cannot find the stable. Yeah, only this case make the system stable. Right? You see. So this condition, the integration of the impulse response smaller than infinite. Now we can state them. Use those poles. If all the poles they have negative real part, then the system is BIBO stable. It is stable. Right? Okay. Let me result. I put it here. If all the poles of G of S have negative real part, the system is stable. Right, so we have this. And if any of the poles, any one of the poles G of S has a positive real part, this case system is unstable. unstable. And we have the third case. If all of the poles of G of S have non-negative real part, and at least one of those poles, and at least one of them has zero real part. We call this case, we call the system is marginal stable or unstable. It is stable. It is unstable in this case. It is unstable, right? It is unstable, as we just discussed. If the real part is 0, you will consider integration of this one, then you get the infinite, right? Because it's t go to infinite, there will be 1 forever. The area below the function, right? That is infinite. So only this case it is stable. These two cases they are not stable. However, this case is kind of special. The poles is in the bound, right? It's larger than 0, smaller than 0. Here is equal to 0. So the poles they are in the bound of these two kind of situation. So we call this case, we call the system is a marginal stable or marginal unstable. All right. Okay. You can check the location of the poles here, or here. So this one you get stable. If you have some poles here, it's unstable. And here is also both cases are unstable. But for this one, we have another name is a marginal stable, unstable. The same thing, but someone call these marginal stable, someone call these marginal unstable. Yeah, but basically, in this case, the system is still unstable. You give some bounded input, the output may go to infinite. All right. So this is the stability, and usually we just check the location of the poles, then we know whether the system is stable or not. All right. Then next question, right? We know we can check the location of the poles to determine the stability. Then if the location of the poles are all in the negative side, right? Then it is stable. Negative side or negative side, right? Otherwise it is unstable or marginal stable if some poles are just in the bound and no poles in the positive side. So the problem is then question. How to find the poles, right? You need to find the poles. What are these poles? Right? Before you check the stability, you need to find these. Or you need to solve it. And nothing special, just to solve it. However, solve a pole is not so easy. You need to solve equations, right? So you solve algebraic equations. If the equations order is 1 or 2, that will be fine. if the order of the equation is higher than 3, like 3, 4, or 5, I think we still have some formulas, but that formulas are very complex, and most of us, we don't know what are those formulas. You search online, maybe you can find the third order equations, third order polynomials, how to find the poles. One, use formula. Use formula. This is for second order. Second order, you let the denominator equal to 0, you can solve it. And then for higher order, it's very hard to solve it, but we can use computer. Use computer to find the roots. In MATLAB, we have a function like this. We can use this one to find the root or roots. Yeah, you need to check your software. You go to MATLAB, you type root or roots of a polynomial, or you type help root or help roots. You can know how to use this function to find the poles of transfer function, or find the roots of a polynomial. Yeah. And okay, then we have another one, third one. This one, we do not need to solve the equation. We do not need to solve the equation. We only need to do some kind of a calculation. Then we can determine, do we have poles in the right side? Right, the thing like that. This method is called Routh-Hurwitz or Hurwitz method. You can check the textbook for detail, and here I use some example to explain it. Alright, example. Suppose I have a system like a g of s equal to 2 of s to the 4 plus s to the 3 plus 3s to the 2 plus 5s plus 10. This is denominator, and numerator 3s squared plus 4s plus 7, for example. Then we want to check this is stable or not. Okay. The system G is stable or not. You want to solve it? It's not easy. I know this is a fourth order actually. It's very hard to solve. This one maybe we still have formula, but when the order is higher than 5, there's no formula. So far, no formula. I think it was proved. No formula. This is really no formula for if the order higher than 5. No formula. Yeah. Okay. Then how to do it? Now we can work like this. We list the coefficients of the denominator in a table. Because this way as actually the table is given by this guy, Routh tabulation. We put, okay, here's order 4. I put s to the 4 and s to the 3. So these two, there are some orders, some powers of s, and then the order is just here. S4, then put S4 here. SQ, then put SQ here. And coefficient. 2, you put 2 here. Then 1, you put 1 here. Then 3, you put 3 here. Then 5, then 10. Okay. Okay. So things like this is 2, Then here's 1, 1, and 3, and so on. Okay. Then you put all the coefficients here. Alright, these are the first 2 rows of the table. Now we check next one. Here you put s to the square. So one numbers, the number is 1 less than here. This is s to the cube, then here's s squared. Actually, we also need s and 1. Every time you will list all these s power of s here. For this example, we start from s to the 4th. Maybe different, like s to the 10th or s to the 2th. Then you will reduce the power along this bar. So s4th, s2 3, s cubed, then s squared, then s, then 1. 1 is s to 0, right? So the order of s decreasing 1 by 1. Then here, this number, what is this number? We look at here. We look at these 4 numbers. So we have this. This is a 2, 3, 1, 5. We calculate the determinant and put a negative in front of it and divide it by this number 1. This number go to here. Okay, and this result will go to here. Alright, we can do a calculation what it is. This one is equal to negative, okay, determinant of this is 2 times 5 minus 3, it is 7. Right, negative 1 times 7, or just negative 7, right? Divide by, this is 1, so here's 1. Okay, have negative 7 here. Negative 7 here. Actually, we already know this is unstable. Okay, I will explain it later. Then we need to calculate this number. What is this number? I still use similar way to find it. The negative of determinant of a matrix divided by this number. But the 2 columns, we use different columns. We use 2 and 1, right? The first column, and this 10 and 0. Here should be 0. We do not have value, that means 0, right? Okay, determinant of this, put negative in front of it, divided by this number. So this is a 2 times 0 minus 10. So 2 minus 10, I have negative 8. And here's a negative, so it's a positive 8. Positive 8. Right? So here's a positive 8. Oh, sorry, 8. Positive 8. But they finish. Right. You have 8. Am I good? Oh, this is not 8. I'm crazy. This is not 8. This is a 2 0. So 110 minus 2 minus 10. 2 minus 10. 2 times 0 minus 10. 0 minus 10. So it's an and negative in front of it, divide by 1. So it is 10. I'm sorry. It is 10. Alright. Okay. So we have this value. And if you want to calculate more, like this number you do the same thing. You need a matrix. And the matrix you need 2 columns. First column still 2 and 1. The other column will be these 2. Here's nothing, that means 0 and 0. So this number is also 0, right? You have a matrix. The whole rows are 0. The whole columns are 0. So the determinant must be 0. So this is 0. If you want to calculate, it is 0. You can just leave it empty here. Alright. Okay. Now we finish one bar, one line. Then we go to next line. the row of the S. We need to calculate this number. How to do it? Similar. We have this formula, but with different row and column. We calculate these. We need this matrix. So I put it here. It's 1 and 5, -7 and 10. Take determinant with negative in front of it and divide it by -7. So every time you need to divide it by this number. Alright. Then result is, this is a negative of 10 plus 35 over -7. So it's a negative, negative cancel. 7. This is 45. I leave it or divide it? Yeah, I just leave it. I can't finish. This is a positive 45 over 7. Alright, then we can work next this number. This number I will use 1 and -7, 0 and 0. So it is just 0. Okay, we're done. Then last one. Let me write here. This part, it is just this one. Alright. Then we calculate next this number. Still same thing, we use this matrix. So this time it is, let me use a different paper. Have the table here. This is this number. We use these 4 to do the calculation. So it is a negative. This is -7, positive 10, 45 over 7. This is a 0, and divided by this number, divided by 45 over 7. Okay. Now we do the calculation. This is a negative. Okay, -7 times 0, we get 0. 0 minus this, so it is a negative 4, 5, 10 times 10, 450 over 7, and divided by 45 over 7. Positive, negative cancel, should be positive. And okay, you see, just 10. It is just 10, right? You cancel 7 cancel, 45 cancel. It's just 0, just 10. So here's a 10. Yeah, that one is from next page. Alright. Okay, we finished the calculation of the table. So now, do you know how to calculate the table? Well, you have a transfer function looks like this. You take the coefficient from the denominator and put these coefficients in the first 2 rows of the table. And here you have a column of S. S fourth, F third, F second, S itself, and 1. Okay, just these. You put it here. And then you need to calculate this part according to this formula. But every time you need 2 different rows. One row, like here's 1, 2, and 1. The next is 3, 5, or 10, 0, or 0, 0. Then you can have -7 and 10, and another one will be 0. Right? Things like that. We know how to calculate. Okay. Then after we calculate, how to determine whether it is stable or not? I will say the first column. We look at the first column. The first column of numbers is this one, at least here. Is 2, 1, -7, 45 over 7, and 10. Right? We have these. 2, 1, negative 7, 45 over 7 and 10. Right? So I just copied them here. And you see, you check the sign. This is positive, this is positive, and this is negative, this is positive, this is positive. So here we have from positive to negative and negative to back to positive. This is a change. Oh, sorry, some car is yelling outside. This is change 2 times the signs of this number change 2 times. Change 2 times. Now we know there are 2 zeros, 2 roots or 2 zeros, 2 poles. Zeros of the equation, but it's a zero of the whole. It's a poles of the whole transfer function. Because there are 2 poles in the right side, right half plane. Right half plane. Right, this is a S plane. And this side is a real part positive. This side is the left side is real part. Real part is negative, right? And here is a real part equal to 0. Right? So this, yeah, we have 2 this side. So this system is unstable. System is unstable. System is unstable. You got it? The things like that. And if there's no change, all of these are positive, then it is stable. It is stable. Can we have a try? But for high order, I give them randomly. I'm not so sure when I give. So maybe next example is also unstable. Yeah, we can try the second order. I cannot. Okay, another example. The system has transfer function equal to s squared plus 2s plus 10 s over this denominator. Stable or not? Stable or not? We check this table. Use table. We give 2 rows firstly. They are 1, 2, 10. Now that's it, right? 1, 2, 10. Only 3 coefficients. And this is s squared, this is s. All the rest, if you want to put all the rest are zeros. Yeah. Okay. Now here s squared, s, then here will be 1, right? Just the 1 reduced of the power. So it should be 1. S to the 0. And this number, what is this number? This number will be 1, 2, and the 10 and the 0. Determinant, put the negative in front of it, and divided by this 2. So this is negative of 0 minus 20 over 2. That's 10, right? So here's a 10. And if you want to calculate these, you need to use these 4 numbers. You get 0, right? Okay, you're done. We check the first column. First column. No change on sign. There's no change on sign. So we say stable. Right? It is stable because there are no poles in the positive side. Yeah, no change, then no poles in the positive side. In the previous example, we have two changes. Sign from positive to negative, and negative go back to positive. We have two changes. Then there will be two poles in the right half plane. So system unstable. And this one, now this one is a stable one. All right. So we can just check it like in this way. By this way, we do not know what is the exact value of the poles. But this calculation is a kind of accurate calculation. If you want to solve the poles for higher order system, you need to use MATLAB, use computer or MATLAB or computer. The solution usually it is just an approximate, so you still have chance to get something wrong, right? It's approximate, not exactly. Maybe the things like some poles they are in the very close to the boundary, but it's still in the right side of the S-plane. It's unstable. But you find the poles by computer. Maybe you find the poles in the negative side. There is some small error, right? It could be happen sometimes. That is so. Just use computer sometimes is not so. You cannot make sure really is really good. The solution sometimes may be some errors. Right? But this way, you can check. You can have a result very. It is no problem because all the numbers you have the exact value. Right? Okay. So this is the Routh method to check the stability. Now we have two ways, right? To find the stability of system, we have two ways. First way, we find the poles. Find all the poles. Then if some in the positive side, it is unstable. All of them in the right side, it is stable. Second method, you just to calculate. You try to find the table looks like this, the Routh table. In this table, you check this column, the first column of numbers. Actually, this is second column, right? First columns are S and their powers, S and its powers. This is the first column of numbers. If there are no change on the sign, the system is stable. If there are some change on the sign, then the system is unstable. Right? Okay. Then we consider we apply this to a feedback system. Now, as we discussed in previous class, a feedback system, that is the most common used structure of a system, and the most of the design work is how to design the control of a system in a feedback system. Now we consider a feedback system. We have a plant G of S, and we have a feedback. We suppose this is unit feedback. Alright, unit feedback. And then we put the controller. Controller is just a constant K. Right. So this is a unit feedback system. Controller is K. And the problem is find K, make the whole system. I say S. Okay, this is R of T, this is Y of T. You see that is a whole system, right? Whole system S of S. Oh, I had both of S. I use T. Okay, I use m. Okay, m of s, which is y of s over r of s. This one. We want to make it stable. Make this one stable. Make this one stable. Alright, use an example to explain it. Suppose g of s equal to, let me give an unstable system. Like here's s plus 2, here's s minus 1 and plus 1. Yeah, just this one. Okay, s squared minus 1, here's s plus 2. Okay, so this is unstable, right? Unstable, because I have poles -1 and 1. This is 1, this is -1. I have two poles. So one pole in the left side, no problem, but the other pole is in the positive side. So this is unstable. G is unstable. Unstable. G is unstable. Now add a controller like that. Okay. Controller like that. So can we find the K? Make the whole thing stable. Whole thing stable. Now m of s is what is the transfer function of the whole thing? We just studied, right? We use the gain formula. This system, we have a forward pass is k times g, and we have one loop. This loop touch the forward pass. So here delta 1 just 1, right? Delta 1 is just 1, and the dirt in the denominator dirt will be 1 minus this loop. So this loop is k times g, and with a negative here. You see, here's a negative. So along this path, k, g, and at this point is a negative. So I need a negative in front of it. So this is plus. In the first exam, I have an example. I give a structure and ask the transfer function, right? I have some summation, 3 summations. Some summations I have both positive and negative. It's a subject, but I have at least one. I think I forgot which one. At least I have one. There's no sign here. That means the summation is really just a summation, not a subject. Yeah. Okay. Now go back to our problem. So now it's a minus. Here's a plus. This is m. And what is a g? We know this is g, so we plug in and do a simplify. Yeah, let me write step by step. K times s plus 2 over s minus 1 and and plus 1. This is numerator. Denominator is 1 plus k times s plus 2 over s minus 1 and s plus 1. Okay, so this one is I times s minus 1 and s plus 1 in both numerator and denominator, right? I can cancel this part. So I have k times s plus 2, right? This part cancel. And over this one times here. So it is s minus 1 times s plus 1 times 1 and plus k times s plus 2. Alright. Yeah, this is m of s. M of s. Now we do some simplify. K times s plus 2. Okay, this is nothing we need to change. I just keep it. And denominator, I will write it in terms just on s, not in terms of these two factors things, right? So we have s squared. This gives us s squared plus 1, and this is a ks plus 2k, and I put them in order on the s, where be s squared plus ks plus 2k plus 1. Right? Here's a k times s plus 2. Am I good? S squared plus minus 1. I'm sorry. Minus 1. So here's a minus 1. Hey, here's a minus 1. S squared minus 1. Minus s plus s cancel. So negative 1. Yeah, s squared minus 1. And this is ks plus 2k. Ks 2k. Okay, we have this. Then we check the table. For this one, you can also solve directly. You solve directly. But here I want to just explain how to use this method. Explain the method. Okay, use this one. I have s squared and s, and the next will be 1, the first column. Then here I put the numbers coming from the coefficient. Here's 1, then is k, then 2k minus 1. Okay, no more. And then we need a calculation here. This will be 1 and the k, 2k minus 1 is 0. And here's a negative. Here's divide by this, right? Divide by this, divide by k. So this is a negative 0 minus k times 2k minus 1. Sorry, this is bound. Over k. Okay, 0 nothing, right? The negative is a positive, and the kk cancel. So this is just 2k minus 1. It's a 2k minus 1. Alright, we have this table. Now we say to make the system to make the system stable. We need because 1 is positive, already positive. We need k is also positive, and 2k minus 1 is also positive. Right? We want there is no change on the sign in the first column. No change. On the signs of the second column, or the first column of numbers. Okay, then we can determine what kind of k can we use. First one, we want k positive. Second one, I can write as 2k larger than 1. So okay, k is still right, and this one means k larger than 1/2. Alright, you want to satisfy both together, right? You want both are positive, so that is k larger than 1/2. Larger than 1/2. You want both have. If it's just larger than 0, then k still have chance smaller than 1/2. Right? We want both satisfied, so k must be this. Okay, so by this k, we can make sure the system is stable. System stable. All right. We can try a different example. I can try different way. Another way is we can also solve it directly from the post method. Method A. Right. We can also use method B. Pose of m of s. Right? I said this is m of s. Right? This is m of s. This system m of s. Poles of these are are the roots of s squared plus ks plus 2k minus 1, right? The roots of it. We need to solve it. Here actually we have a name. This is the denominator of transfer function. We'll call this as a characteristic polynomial of m of s of the transfer function. It is a name. If you read that book, you can see. Then what is the roots of it? Yeah, this is the second order. So the roots are denominator will be 2 times a, right? And here will be negative b plus or minus square root of b squared minus 4ac. Right? This is the I follow the formula for the second order polynomials, how to find the poles, how to find the roots, right? This is this one. So these are negative k plus or minus square root of here's a k squared minus 8k and plus 4. I'm good? Yeah. And divide by 2. Okay, so you look at this one. Can we know it is stable or not? Or you need to check the value here. What is the value of this? This one is k squared minus 8k plus 4, or depending on k. If k is large enough, this is a real number. This is a real number. If k is smaller, this might be a negative number. Then square root you will have a j. You have j, and right here. If k squared minus 8k plus 4 positive, then we have the roots 1 and 2, right? Roots 1 and 2. So I will say roots 2 equal to negative k minus the square root over 2 is a smaller than 0, but root 1 is negative k plus this is a something. Whether this is a positive or negative, you need more details discussed, right? I just leave it here, So here you see, it's the question is you still can solve it, but the way is you need a lot of detailed works. Here you still need to check this part. You want to make sure this part, negative k plus this part, it is a positive or negative, right? You need to solve this. Solve this to find what kind of k. If this is a positive, then it's unstable. So you need to choose k, make this part is also negative, right? Yeah, so this is this case. And if k squared minus 8k plus 4 is smaller than 0, then you want negative k plus 2 and plus minus, here will be 2 square root of k squared minus 8k plus 4. This part is this is an imaginary part, right? Imaginary part, and this is a real part. So this one you want k larger than 0, make stable. Okay, this is like the first condition when we use the table method, right? In the table method, we have in table method we have these two conditions, right? One we want k positive, another one we want k is larger than 1/2. Right here you see we get the condition k larger than 0, and then another condition we need this, I think. From here, you do some calculate, you can see if k is smaller than 1/2, this one take square root or larger than that k and make this positive, then it's unstable. Yeah. I will not do it, but you know how to do it, right? You know how to do it. And actually, I don't recommend this way to do it. Right? You use a table is fine. Your table is fine. Okay, so this is one example. You can try some high order. Let me see. Yeah. Another example. We can try high order. We consider this one. This time we consider system looks like this. I said this is a k, and also I have another one. It's a 1/s here. Only when this is a constant k I use triangle. Otherwise I use a square. Okay. And this is a k. This is a k1. This is k2. Is it clear? This is a 1/s times k2. This is k1. Do summation here. And then go to the plan. Plan is g of s. And here we have a feedback. The feedback is still unit. R of t is y of t. You can see this. This kind of feedback system, you know, the controller we have two parameters. One is just constant, the other is a constant times 1/s. We have, this is a PI controller. I this integration, and the P this one proportion, right? Proportion. Yeah. So this is a PI controller. Then here we suppose g of s equal to like s cube plus like a. Here just s. I suppose this one. G of s is this one. It is stable. I would say it is not stable. But if you just look at it, you do not know. So first thing we want to check, is g of s stable? We use a table, Routh table, RUTH. I have s cube, s square, right? Then s, then 1. Here's s cube is 1, no s square term, no s term, then constant term. Okay, now we want to check this value. This value will be 1008 divided by 0. Here's minus. Oh, this is a terrible case. We divided by 0. We cannot do that. Then we have a kind of way we can change it. We replace this, use epsilon. We write this as a epsilon, small epsilon, right? Small number, epsilon, larger than 0 and small. So this is this one is also epsilon. So I have 1 epsilon 0a negative over epsilon. I have this. Then this one will be negative 1 times 8 minus 0, right? So just like this, and divide by epsilon. So here is a negative 8 over epsilon. Alright, we're done actually. Unstable. Unstable. Because this is a negative, right? Positive, you can think 0 is also positive. It is a number, a very small number, but positive. But next is negative. So you already know it's unstable. Unstable. Here we have a change on side. At least one change, right? If you calculate the next number, maybe go back to positive. I don't know. I just leave it here. That'll be fine, right? Okay. So G itself is unstable. G itself is unstable. If you want, you can find the roots of this one. Poles of it, it will be something like this. One is is a 2. Yeah, negative 2, right? Just negative 2 and 2 are here. It looks like this. Alright. Okay. Then we try to find K1, K2 to make the system, the whole system, stable. Here the transfer function of the overall system, I write is m of s, which is y over r. I put over input. Okay, here we check. We use the gain formula. We have this part you can just merge it together. It is a summation, right? It is a summation. It is just a summation of this one and this one. So the forward gain is K1 plus 1 over S K2 times G of S. G of S. This is a forward pass, and only one loop. One loop touch the pass, so here's just 1. And then the denominator, I need 1 minus this loop. It is still this one. K1 plus 1 over S K2 times G of S. And the loop here I have negative, so it's this one. Okay, so this is m of s. Now I plug in what is G. G is this. So this is a K1 plus 1 over S K2 is S over S cubed plus 8 over 1 plus K1 plus 1 over S K2 and S over S cubed plus 8. Okay, and to simplify, I times this S cubed plus 8 in both numerator and denominator. Now numerator terms to be, I times S cubed. Is that enough? Yeah, just time this is fine. So it is K1 plus 1 over S K2 times S, and here is S cubed plus 8 times 1 and plus K1 plus 1 over S K2 times S. So this gives us, I multiply S inside is a K1S plus K2 numerator. Denominator I have S cubed, this is constant. I put the S term here. This is a plus K1S, and then constant term. This is A, and plus K2. All right. Can we have these stable? Can we find K1, K2 make this stable? All right. We use the stable. Oh, I don't have time. I think I need okay, I think I can finish just like this. Give me several minutes. Alright, as cube, as square, then here's a 1, then 0, as square term 0, then k1, then a plus k2, like this. And similar, I replace these by epsilon, and then I calculate, this is 1, this s and 1, right? I calculate this number, it will be 1, 8 plus k2, and here's k1, this is epsilon over epsilon is negative, equal to is 8 plus k2 minus, this is epsilon k1 over epsilon, and the negative in front. So this gives us negative. I put the positive in front, so positive. So this is k1, right? This part give us k1 and minus 8 plus k2 over epsilon, right? And this will be 0. And this will be 8 plus k2. Yeah, you can try. Alright, to make it stable, we need this. To make M of S stable, we need k1 minus 8 plus k2 over epsilon positive, and 8 plus k2 positive. We want these two. Alright, so we want these two. So here, let me see. This positive, this is also positive, and epsilon is a small number. Oh, this is still not good. Sorry, we can't because epsilon is small, so this one will be very is a negative side, very large negative side, you know. Yeah, this part will be very large, so this part is hard to make it positive. If this is a positive, then this will be a kind of a very large negative value. So it's hard to find k1, k2. Okay, this is not a good example. It is an example you to explain the problem, but the answer for this example is hard to find the parameter. Alright, yeah. Okay, that's all for today, and you can check the what is the homework problems from the Blackboard. Okay, and that's all for today. Bye bye. Sorry for